To make effective and targeted changes to maps stored in the control unit of Harley-Davidson motorcycles, it is necessary to understand the basic structure of the program running in the fuel injection control unit. The control unit of the motorcycle contains an application, a basic control program with a numerical identifier. Versions may differ based on the region where the first sale of the motorcycle took place or based on the latest update. The application is a control program that manages the running of the engine. It reads information from sensors and controls all actuators. The Diag for Tune program provides only one selected application for any given motorcycle. The goal has always been to use an updated and stable application. An important part of the application is calibration. In essence, it is a system of parameter tables. Calibration uses these parameters to control the specific engine. Parameters listed in calibration have two crucial roles. First, to describe the mechanical, pneumatic, and hydraulic parameters of the engine. In this case, these are VE maps, engine displacement, and injector flow rate. It is necessary that these parameters describe the real state of the engine that is to be controlled. The reasons are described in detail in our video titled Why Perform Tuning. Second, to allow adjusting parameters which dictate how the injection control system regulates combustion inside the engine. These are the AFR Target Map, Ignition Advanced Maps, and all other parameters except for those listed in the previous point. Parameters listed in calibration tables are divided into three basic groups. The first group is fuel maps. These maps are the basic target for optimization, and their structure and methods of adjustment will be described in detail later. The second group is Ignition Advanced Maps. We recommend leaving these maps unchanged. Optimizing these maps is very technically demanding and is beyond the scope of this training. In most cases, unless the engine has undergone major overhaul, the benefit of adjusting these maps is minimal. If the engine is used on a territory where fuel with a lower octane rating is available, often in connection with the high ambient temperatures, combustion in the engine cylinders may be detonative. The solution to this problem is careful reduction of the ignition advance in the problematic areas of the map. The third group is Other Parameters. The control unit encompasses a wide range of parameters. Diag for Tune provides access to a selected portion of these parameters necessary for efficient tuning of the engine. A more detailed description and recommended settings will be described later on. This brings us to explaining fuel maps, the main target of optimization in the Diag for Tune software. VE maps differ for each engine cylinder. It is one of the basic properties of two-cylinder longitudinal V engines. VE means volumetric efficiency. The value indicates the volume of air that each cylinder can take in. The VE value denotes the ratio of the air actually taken in divided by the displacement of the cylinder. The value is stated in percent. Of course, the percentage is dependent on the opening of the engine's throttle valve and on engine speed, or RPM. As a result, there are always two different tables for each cylinder. Older models generally use tables dependent on parameters TPS, which stands for Throttle Position Sensor, and RPM. Newer models generally use tables dependent on parameters MAP, Manifold Absolute Pressure, and RPM. Configuring the MAP/RPM set of parameters is better for tuning the running of the engine. Pressure in the intake manifold better defines the amount of drawn air in relation to changes in barometric pressure. The most important thing we need to know about VE maps is therefore: first, VE maps describe the capability of each individual cylinder to take in air. Second, there are only two ways to properly tune VE maps, and these are by no means manual changes that reflect the wishes of the owner of the motorcycle or of the tuning operator. The first and most accurate method is setting up new VE maps by measuring the motorcycle at load. This method is suitable for correspondingly equipped tuning centers with an experienced operator, and the process is quite time-consuming. But the results of the optimization are guaranteed. In Diag for Tune, this process is called professional tuning. The process of VE measurement on a testing bench can be seen here. Actia includes training in VE measurement on a bench as part of a sale of the Smart Power Bench product. An alternative to measuring VE at load is to road test, where the motorcycle is instead tested and measured when driving. The basic procedure can be seen here. The second method is setting up VE maps by selecting a correct VE map for the given type of motorcycle and its specific intake and exhaust configuration from Diag4Tune's map database. In Diag4Tune, this process is advanced advanced tuning. A detailed description of the process is provided in the next chapter of the training. What to say about VE maps in conclusion? If your aim is to increase the performance parameters of the engine by modifying the motorcycle's intake or exhaust system, then VE values in measured maps are the best benchmark. Increasing VE values in some aspects by, for example, 10% means your modification succeeded in increasing the volume of air in the cylinders by 10%. It also means you have created the prerequisites for increasing engine torque by the same amount. Accurately measured VE values are thus the most important indicators for any tuning operator. Their greatest benefit is the fact that they describe the performance behavior of the engine across the full spectrum of the engine's operating modes simultaneously. Often, other presented engine performance characteristics describe engine behavior exclusively with the throttle valve fully open. Now let's take a look at the second part of fuel maps. The AFR map, otherwise known as the AFR target map. The map allows the operator to adjust the air-fuel ratio in all engine modes. A motorcycle only has a single map which applies to both cylinders at the same time. The process of adjusting this map should be on purpose and based on the operator's experience. First, let's recall what an AFR, in other words air-fuel ratio, is. The AFR value indicates the mass ratio between the air and the fuel in kilograms present in the combustion process per engine cylinder cycle. The mixture of air and fuel in the cylinder is combustible or ignitable approximately within the 12 to 18 AFR range. However, there is one AFR value in particular that is very important. It defines the ratio where a full chemical reaction, in other words oxidation by combustion, takes place between fuel hydrocarbons and oxygen in the intake air. The result of the chemical reaction is water and neutral gases, namely nitrogen and carbon dioxide. From the perspective of emissions, this neutral ratio is known as the stoichiometric ratio. For gasoline fuels without additives, the stoichiometric AFR is 14.6. Fuel combustion at stoichiometric ratio minimizes emissions from the engine. The catalytic converter mounted in the exhaust manifold is only truly effective when the engine works with a fuel mixture at the stoichiometric ratio. An engine operating with a mixture at this ratio also achieves the lowest fuel consumption. It holds that at AFR over 14.6, the engine works with a lean mixture. At AFR lower than 14.6, the engine works with a rich mixture. Long-term engine operation with a lean mixture causes slowdown in combustion speed of the mixture and increases temperature in the combustion chamber. Combustion of the mixture continues into the exhaust cycle around the valves and into the exhaust manifold. Temperature in the combustion chamber rises. The running of the engine is often unstable and there is a risk of damaging the valves and overheating the exhaust manifold. Combustion of a slightly rich mixture increases engine torque and reduces the temperature in the combustion chamber. At the same time, however, the engine's fuel consumption increases. A very rich mixture washes off the lubricating oil film from the sides of the engine cylinders and increases mechanical wear. Carbon forms in the combustion chamber and the exhaust tract. Unburdened mixture continues combusting in the exhaust manifold, which begins to overheat heavily. It is important to mention at this point that there is another definition of air-fuel ratio known as lambda, which denotes the excess air coefficient for combustion. The stoichiometric ratio is represented by lambda value of 1. An indisputable benefit of this method of expression is independence on the type of fuel. Maps of newer Harley-Davidson motorcycles do not express air-fuel ratio through the AFR value, but through lambda. However, Diag4Tune allows you to display the air-fuel ratio as you choose. regardless of how it is defined in the fuel maps of the injection control unit. It holds for the excess air coefficient that, if lambda is over 1, the engine is running on a lean mixture. If lambda is under 1, the engine is running on a rich mixture. Now, to have an example, let's describe and discuss the original AFR map of a Sportster 2007 XL 1200 motorcycle. The situation is similar with other models. A large portion of the map is filled out by the requirement for AFR of 14.6. That means that it is required that the engine run at the stoichiometric ratio and under closed-loop control. This area covers the majority of the motorcycle's operating modes. Working under closed-loop control means the amount of injected fuel is adjusted by measuring the real air-fuel ratio by an oxygen sensor to ensure that the engine runs at the stoichiometric ratio. The oxygen sensor, also known as the lambda sensor, is built into the exhaust manifold near each individual engine cylinder. In other areas of the AFR map, where the required AFR values are lower than 14.6, the system operates under open-loop control. That means the system controls the air-fuel ratio solely based on fuel maps and ignores information about the real ratio from oxygen sensors. So how does this all work in an engine in modes where the AFR value is set to less than 14.6? The control unit knows from the VE map for the front cylinder how much air has been taken into the cylinder. It knows the desired air-fuel ratio from the AFR map. Based on this data, the control unit calculates how long the fuel injector for the front cylinder has to be open. It will do the same for the rear cylinder fuel injector, but using VE map data for the rear cylinder. If we are in an area where the AFR value in the map is set to 14.6, the calculation also factors in the results of measurements from the oxygen sensor. That means that at AFR 14.6, the system operates under closed-loop control. Some motorcycle models are equipped with an injection control unit but not oxygen sensors. For these models, the AFR value of 14.6 is replaced by 14.5. This setting essentially still maintains the stoichiometric ratio. The difference in value is minimal. However, having the value set to 14.5 eliminates the oxygen sensor from the equation. So far, we have described the area of the AFR map where the air-fuel ratio is set to 14.6. The 90 to 100 map area, in other words, the area where the throttle valve is very open, is set to AFR value 12.5. In this mode, the engine is set to run at maximum performance and usually does so only for a limited time. The mixture is thus set to very rich ratio so that the excess fuel can be used to cool down the combustion chamber and valves. We find a similar area in the 5,000 to 5,500 RPM region, where AFR is also set to 12.5 for the same reason. The last area with a rich mixture can be found in the map 20 to 25 kPa region. This area of the map defines the behavior of the engine during deceleration and is generally responsible for the so-called backfire. This phenomena usually occurs when the engine works under lean conditions due to the installation of an open exhaust or due to the intake valve being open. The fuel mixture may then teeter on the edge of the ignition threshold in certain deceleration modes. Irregularity of ignition of the mixture results in the exhaust manifold occasionally taking in unburned fuel. The subsequent function cycle causes ignition of the accumulated unburned mixture in the exhaust system, which then manifests as a noticeable, undampened detonation or chain of detonations. Suitably adjusting the AFR map allows us to optimize performance parameters in relation to the economy of engine operation. We are also able to greatly increase driving comfort and eliminate certain unstable driving modes. Adjusting performance settings also allows us to curb backfires. This optimization of performance parameters is based on results of performance measurements on a twin-cam engine. The following characteristic shows the measured dependence of maximum torque in the 2,500 to 3,000 RPM region of The following characteristic shows the measured dependence of maximum torque in the 2,500 to 3,000 RPM region on AFR setting ranging from 11 to 15. The measurements were made for 60% and 100% throttle valve opening. The black characteristic curve represents the chosen average. The characteristic shows that the 14.6 AFR region is optimal in terms of emissions and fuel consumption, but is not optimal in terms of performance parameters. By adjusting AFR to around 13, we automatically gain an increase in torque. However, changing the setting across the board would result in increased emissions and fuel consumption. The map system in Harley-Davidson motorcycles does not allow switching between maps, as needed while driving, so we looked for another solution. Road tests have shown us that driving in the city or on the road generally uses map of around 60 kilopascals, where the original settings are the most optimal. The situation is different, however, when it comes to acceleration, for example when overtaking another vehicle. In these cases, map is in the region of 70 kilopascals and above, and the need for increased performance parameters is also desirable for the sake of safety. These experiences have led to the design of what we call an AFR dynamic map. The map has static values but behaves dynamically. Under standard operation conditions, in other words map no higher than 60 kilopascals, the engine works with a stoichiometric AFR. If the throttle valve is more open, in other words map of 70 and above, the engine automatically switches to an AFR that provides maximum possible torque. The AFR dynamic map therefore operates as if it had an automated switch. Of course, the 60 to 70 kilopascal threshold can be moved around to achieve the desired effect at a different map range. Adjusting the AFR map for improved driving comfort. A general requirement on the part of bikers is driving in low RPM modes, where the V-twin engine has the best sound. However, shifting at low RPM causes the engine to temporarily enter into an unstable operating mode. Therefore, it is best to set the very low RPM region of the map to a rich mixture as indicated here. In these cases, the changes in the emission behavior of the engine is minimal, but driving comfort increases significantly. This setting even allows using higher gears at very low RPM. Adjusting the AFR map to eliminate unstable engine behavior. This specific example applies to Evolution engines. Once an open intake and exhaust system is installed, the running of the engine can often become unstable during normal drives in city traffic. This behavior manifests at around 50 km per hour on third gear even after optimizing VE maps on a test bench. Measurements have shown the area in which these instabilities occur, as shown in the map here. After testing, it was found that the cause is an unstable oxygen control loop in the controller unit's program. The issue is thus not a mechanical malfunction, but a system error. The adjustment to the AFR map that suppresses this behavior is indicated here. The setting deactivates the oxygen control loop in the unstable area, and an enriched fuel mixture completely eliminates the negative behavior. The next example showcases adjustment of the AFR map to eliminate the above instability in a Sportster XL883 motorcycle. The only difference here is the area where the instability occurs. Dynamic maps and some of the typical corrections to eliminate instabilities are already pre-built into the Diag-for-Tune system for the majority of motorcycle models. These adjustment procedures can be useful as a guide on how to eliminate unstable operating modes not only in Evolution, but also in twin cam and other engines. So far, we have presented AFR of 14.6 as a stoichiometric ratio. This ratio applies to our average gasoline without a major addition of alcohol. The present table shows how the stoichiometric ratio changes based on alcohol content. The effect is significant in E5 fuels. Similarly, the effect is borderline negligible in E10 fuels. But for fuels with E15 and above, making adjustments is more than advisable. To make these adjustments, we recommend using a mathematical physics trick that leaves the fuel maps numerically unchanged. We do so by applying correction factor for engine displacement that changes the displacement by the percent listed in the table here. Finally, let's take a look at the last section of calibration called Other Parameters. A rev limiter protects the engine from damage caused by so-called over-revving. You should not increase this limit unless you can at least increase the movement speed of valves by using corresponding springs. Idle speed is controlled by the idle speed characteristic based on engine temperature. It is advised to modify this characteristic if the engine shows RPM instability during engine warm-up. First, identify the problematic temperature areas using Diag4Bike diagnostics. Then make adjustments to these areas in maps called Warm-up Enrichment and IAC Steps Warm-up. Acceleration Enrichment. From our experience, it is best to increase the parameters for dynamic mixture enrichment by 5 to 10%. Setting up dynamic control for an electronically controlled throttle valve primarily applies to Touring 2008 to 2016 models. The original map places major restrictions on the relationship between the position of the throttle handlebar and the position of the throttle valve at low engine speed. The manufacturer's goal was to limit the onset of performance parameters of the motorcycle during acceleration. It is likely used as a method to protect the clutch and transmission. However, the setting spoils the enjoyment from aggressive acceleration of the motorcycle. This map gives the tuning operator the ability to set up their own custom characteristic. As a guide, Actia offers a new setting in this map, Aggressive Throttle by Wire. This setting greatly increases the acceleration capabilities of the motorcycle while maintaining a certain degree of protection of the motorcycle's mechanical components. It is strongly advised to save all settings and changes you make to maps under a custom name in your PC. If you want to set the values to take effect on the motorcycle, you must then load the modified calibration settings into the control unit using Diag4Tune. Though motorcycle tuning may seem complex at first, Diag4Tune makes it very easy. You will see how in the next video.